In this presentation, we show how at the Fraunhofer Heinrich Hertz Institute we established a laser link over 3 kilometers using the principle of multiple inputs or multiple outputs to increase the robustness of the communication. The reported measurements are from February 2025. The link was set in Berlin, where on the left a multi-aperture terminal or MAT was placed on the Heinrich Hertz Institute's building. On the other side, a single aperture terminal or SAT was kindly hosted by Deutsche Telekom on their building. The MAT has actually 4 apertures. Other lenses that we see in the middle are used just for initial alignment. 10 gigabit per second were transmitted with on-off keying in both directions. Each of the 5 apertures transmitted a class 1 laser beam with the same optical power in order to have the same performance in both directions. So how can this configuration increase the robustness of the free space optical link? We first need to know that the atmosphere always has some degree of turbulence, and as the beam propagates, multiple random spatial modes appear. Typically after about 1 kilometer or more, scintillation is significant, and the received beam intensity fluctuates in space and time. Fluctuations are in the millisecond scale and span over several centimeters. You may want a large receiving telescope to avoid the energy holes in the beam, but we'd rather use small optics to simplify the coupling between telescope and single-mode fiber. In that case, we need several of those small telescopes to increase the total antenna size and to provide spatial diversity channels on the scintillation pattern. We now have created an additional complexity, which is the necessity to combine those diverse channels. Our approach here is to detect each diversity channel and to perform the combining digitally. Now, since we want a bidirectional link, we also transmit through the telescope array. Each telescope sends a copy of the original data. The multiple beams will then be combined at the receiver on the left side. The reported 3 kilometer link is essentially a reciprocal channel since the propagation time is negligible compared to the fluctuations. So we expect the signals in both directions to be, if not identical, at least of the same quality. Reasons for discrepancies are the slightly varying components and the slightly different wavelengths that we use in both directions. Nevertheless, channel diversity does not rely on reciprocity, and that is an advantage over adaptive precompensation techniques when dealing with non-reciprocal channels. We recorded the bit error rate for the 4 individual diversity channels and for the combined channel. The bit error rate is shown here for the downlink over a time span of 6 hours in the morning, showing the fluctuations before and after sunrise on a sunny day. Each bit error rate sample is estimated from a bit sequence of a few microseconds and thus can be considered instantaneous compared to fade durations. With 1 bit error rate sample every 50 milliseconds, the statistics of the fluctuations should be here well covered and representatively displayed. The bit error rate ranges from 0, that is error-free, to 0.5, which means a complete signal loss. Clearly, one can see how the link deteriorates as the air gets warmer. Whether it is for the colorful samples of the 4 individual single telescope channels or for the black samples of the digitally combined signal. On the right-hand side, the cumulative histogram shows the distribution of the measured bit error rate values, where the x-axis gives the probability that the bit error rate is higher than the y-axis values. For example, the probability that the bit error rate is at least 0 is always 100%. Or looking at the signal loss for the diversity channel 1, in blue, we read 5% of the time. We do not use forward error correction, but if we consider a hypothetical FEC threshold, above which errors cannot be corrected, we read here for the combined channel in black an outage of 0.3%. The same was recorded for the uplink. The bit error rate samples of the uplink are not synchronous with those of the downlink, so no precise conclusion on the reciprocity can be drawn here. Now, to better evaluate the performance of the combining, we are going to zoom in this time series over time spans of 30 minutes, where statistics are more stationary. So in the night, here about 1 hour before sunrise, the black combined channel is essentially error-free. Some diversity channels experience some signal losses, but in fact, for some reason that we'll explain in the next slide, channel number 2 in orange is much better than the others and is mostly responsible for the overall good performance of the array. As time goes by, fluctuations increase and more errors occur. We have introduced here a gray curve, which is the post-processed selection combining of the individual channels. Basically, we picked up the best bit error rate at each sampling time. It does not correspond to a real generated signal, but it is a good sanity check. Our real combined signal in black is based on the SNR estimation of the diversity channels and on their weighted sum, much like the optimal maximal ratio combining. Here the combining is quite efficient and the real black signal is better than selection combining. With the typical FEC, we could be error-free. As we move on in time, the combined signal suffers from high bit error rates, even losses, and during these deep fades, the hypothetical selection combining, the gray line, performs better. Actually, under strong fluctuations, maximal ratio combining and selection combining are expected to perform similarly. We can also compare with the outages of the diversity channels. For example, the signal loss probabilities are 2, 4, 4, and 20%. Ideally, if the 4 channels were statistically independent, the probability for all of them to fail would be the product of each channel outage rate, that is 6 times 10 to the power of -6. With a measured 3e minus 4, we are still significantly higher. The statistical error is not quite negligible, but more critical reasons for this discrepancy are some significant residual correlation between the diversity channels and some implementation penalty probably related to clock recovery, which would explain the discrepancy with respect to the offline selection combining. If we look at the outages with the typical FEC, we found an outage around 20% for one diversity channel, which drops to 1% for the combined signal. Interestingly, at FEC threshold levels, the implemented real-time combining in black performs slightly better than selection combining in gray. A more general result from those measurements is that to mitigate scintillation over these 3-kilometer link before sunrise time, 2 apertures would be enough. However, under strong turbulence, the 4 apertures are not enough. Performance can also be evaluated by looking at the plane of the multi-aperture terminal, MAT. We see here the 4 apertures color-coded in the same way as the measured diversity signals. The apertures have an effective size of 2 centimeters and are separated by about 12 centimeters. Depending on the turbulence strength, different behaviors of the system are observed including the optical tracking system. What is shown here is a typical strong turbulence intensity pattern. And it turns out that when turbulence gets weaker during the day, the size of the received beam decreases. The so-called beam spread caused by turbulence decreases. This leads to the apertures being at the edge of the received beam. This also means that the SAT, or single aperture terminal, can now spatially resolve the MAT's four beams, and looking for the brightest direction, it's going to drift and track on a slightly stronger aperture signal. For example, it will point to the orange aperture. We currently don't see this process as a problem, since under weak turbulence, we do not need all of the four apertures. At a more abstract level, the goal is to build a free space optical bridge with a flexible architecture. The bridge we present here is not fully transparent, as it involves standardized transceivers, SFP+, and related digital processing, DSP. But these can be easily upgraded to other transceivers, provided that they offer DWDM capabilities. The number of apertures and diversity channels can be scaled also easily. What is shown here is a 1x4 multi-aperture link. This asymmetry is typically what you would have for a satellite ground link, with the multi-aperture terminal being located on ground. Bear in mind that for simplicity, many components are not shown here, like amplifiers, filters, and tracking systems. More details on the implementation can be seen in this paper. So starting from the left, the fiber signal in red is converted to another wavelength in yellow and radiated over a single telescope. Now, the receiving antenna is assumed to be in the far field of the transmitter, so that each telescope of the array is illuminated by the received beam. What we show here in pink is actually the field of view of each element. The diversity signals are then detected, digitized, combined, and we forward the data at the desired wavelengths, here back in red. In the reverse link, we reproduce the signal at 4 different wavelengths, and we duplex them over a circulator. Now note that for satellite links, the duplexer would be significantly more complex than just a circulator, because there is a point-ahead angle that needs to be applied. So the 4 wavelengths are received, demultiplexed, and again digitized and combined. The original signal is then forwarded. Although the 2 antennas are different, we have 4 diversity channels per direction, and the DSP modules are identical on both sides. For terrestrial communication, you may want symmetrical antennas with, for example, a 2x2 configuration. We haven't tested it, but the principle is similar to the 1x4 configuration. Here you emit the signal over 2 different wavelengths, and after propagation, both wavelengths reach each telescope, after which they are demultiplexed. The 4 diversity channels are then combined, and for the reverse direction, the same using 2 more wavelengths. Also in this configuration, 4 diversity channels per direction, same DSP on both sides. So in conclusion, we showed that a multi-aperture antenna is an effective technique for mitigating optical turbulence perturbations. The verification was done with a real-time bidirectional transmission over 3 kilometers with SFP+ modules. As possible next steps, time diversity can be exploited, especially if additional robustness is required and we cannot afford more apertures. However, time diversity will introduce latency, as large buffering is required to overcome the long fades. We may also introduce some adaptivity in the allocation of wavelengths, either for diversity channels or for multiplexing channels. We have seen that not all apertures are necessary during periods of weak turbulence, so why not use wavelength channels for multiplexing in order to increase the data rate? With that, I'd like to thank you for your attention, and here's some contact in case you have cooperation opportunities.